Good morning, good afternoon, good evening, whichever is applicable to you. Welcome to part B of chapter 6, electronic atomic electronic structure. In part A, we went as far as section 6.4, the wave nature of matter, determination or calculation of the wavelength of matter. Today, I want to start off from section 6.5. We will navigate the remainder of the chapter through section 6.8, electron configuration or electronic configuration of atoms. What you see on the whiteboard is basically the models of an atom. And in chapter 6, we're going to look at the atomic structure. How are the electrons arranged in an atom? What I do have here is an illustration of an atom. It's like a sphere, okay? And we assume that we have electrons here. Based on the observation in the 17th century, several scientists attempt to explain or paint a picture of the model of an atom. And what you see on the whiteboards are a sequence by which different scientists proposed the model of an atom. This is John Dalton was the first. John Dalton was the first scientist to theorize. It was just the theory on what the atom is all about. And he didn't paint any picture, but he theorized based on the observation, followed by John J.J. Thomson, Ernest Rutherford. He came up with a nuclear model, and where we are right now, which is the subject of section 6.5, quantum mechanics of atomic orbitals, is quantum mechanical model of an atom. It's important to have a connection from point A, B, C, D in the development of an atom. I know you covered this in Introduction to Chemistry, but John Dalton, all right, he theorized. He just came up with a theory on what an atom is, and basically, based on the observation, he came up with a conclusion. We have about 5 postulates which he theorized, and this is elements are made up of extremely tiny particles. Atoms of the same element are identical. When we mean, or what we mean by element here, are the element on the periodic table. Okay. Postulate number 3: atoms cannot be what? Subdivided. It cannot be destroyed. And we know atoms of different elements combines to form different compounds. 2 of these theories actually, postulates, do not hold any longer. For example, we know we have atoms of the same elements having different number of neutrons and subsequently different mass number because of different subatomic particles, which we looked previously, all right? Thomson, all right, painted a picture that an atom is basically homogeneous distribution of positive and negative charges, of which positive stand for protons and negatively charged, or you see on the sphere here, represent electron. This is what it is proposed. We call this Plum-Bardeen model of an atom. And he said, an atom contains negatively charged subatomic particles, which we call what? Electrons. Positively charged are protons. Ernest Rutherford took this model, and by bombarding positively charged particles, he revolutionized or changed the model of an atom. And this is the part of what we call the nuclear model of an atom. He proposed that an atom is basically tiny, or it's just made of a tiny dense region we call the nucleus. but most of the space is just empty. And outside the nucleus, we have electrons. Now, where we are right now with the model of an atom is the quantum mechanical model, which is the subject of section 6.5. This is the basis of the modern understanding of the atom. I had just to go back to the beginning, how we ended up with the description of the current model of an atom. It started with Dalton's proposal, J.J. Thomson, Ernest Rutherford, the nuclear model of an atom, and where we are right now is the quantum mechanical model of an atom. And these models just explain that electron occupies certain allowable energy states, just like the standing wave, just like the standing wave. Without wasting my time, let's just dive to section 6.5 and have in mind that electrons in quantum mechanical model, electrons in quantum mechanical model of an atom only occupy certain allowable what? Energy states, which we call atomic what? Atomic orbitals. There is a difference between, let me just describe this. When we say orbital, this is a region. This is just a region of space in an atom, where there is high probability of finding what? Finding an electron. That's how we describe an orbital, atomic orbital. Some authors explain this as, region within an atom where there is over 90% of finding an electron. It's different from this orbit, all right? Orbit, this is just a circular path around an object. It's just put it what around an object, So don't think that do not think that an orbit is the same as orbital. Orbital is with reference to a region within an atom where there is likelihood of finding an electron, where it's just an orbit. It's just a circular path around an object. Now, from the wave function, the solution of the wave equation is what we call the orbital, the particle nature. We solve that in quantum mechanics. If you look at this 3-dimension region of space, the shaded blue represent, if you look at this represent a region of space within an atom where there is likelihood of finding an electron. The solution of wave equation developed by Srochika, we call Srochika equations. The equation is beyond the scope of this course, is the Hamiltonian operator square. Okay, these represent the region of space where there is high probability. The dots represent high probability, the region within an atom where there is likelihood of finding an electron. And I define this region of finding an electron is called orbital, okay? The solution of the wave equation is the orbital. The square of the wave function give the electron density. But I see the probability where there is a likelihood of finding. This is the square of the wave function. We will not dive into in details into solving the wave equation, but I just want us to understand what an orbital is. Solving the wave equation give a set of wave function or orbitals and their corresponding energies. Remember energy level 1, energy level 2. We will see that and describe each of those energy level within an atom. An orbital, all right? An orbital is described by a set of quantum numbers, I will equate the quantum numbers as your address. For example, you know, if you order something online, probably Amazon, you have to put in your information, such as maybe house number, maybe the apartment number, the zip code. All those numbers describe where you can be located. We could have several people living within the same apartment complex, but the apartment number will identify where there is likelihood to find that individual. So likewise, the quantum numbers describe the orbital. And remember, orbital is a regional space where there is the likelihood of finding an electron. There are four sets of quantum numbers. There are four sets of quantum numbers, and the first one is the principal quantum number, and it is represented by letter N. This is what we saw earlier on, okay? This is what we saw earlier on in Dalton's, not Dalton, but John Dalton model of an atom when he was explaining that the transition, when we have this, there is energy level 1, energy level 2, energy level 3. These represent N value. It represents the energy. This is N1, this is N1, N equals to 2, N equals to 3, and so forth, moving away from the nucleus. So we call this nucleus, and of course we know we have the protons. So N represent the principal quantum number and is designated using letter N. It takes the values N equals to 1 or 2 or 3 all the way to infinity. We call this principal quantum number. It cannot be 0, but 1, anything greater than. If you understand, this means greater than. This is Bohr's model, okay? Not Dalton, but this is Bohr's model, which we saw earlier on, that energy level 1, energy level 2. When Bohr was explaining the line spectra for hydrogen atom, he explained that the transition from higher energy to lower energy, transition of an excited electron from higher energy to lower energy level, give away photons of light, or a photon corresponding to characteristic color depending on the wavelength. So N equals to 1. Now, second quantum number is called the angular momentum, and it represents the shape of the orbital. It takes the values L, it takes the values, all right, 0, 1, 2, 3, all right, all the way to maybe 4 here. So values for this, you want to know, is take 0 all the way to n minus 1, all the way to n minus 1, depending on the energy level. So if it is energy level 3, L values will be 0, 1, and 2, because the last one is n minus 1, n minus 1. So this is the L value, all right? This is the value, I wanted to say value here, and corresponds to S, P, D, F, G. What you see here, these are just the what they use to describe the kind of lines on the line spectrum for hydrogen. If it was a sharp, they call it sharp, diffuse, and so forth. But remember, the angular momentum represents shape, and the allowed values ranges from 0 to n minus 1. Let's understand what this means. If you are given, if n equals to 5, possible values of L will be 0, 1, 2, 3, and 4, because it's going all the way to n minus 1. If n equals to 3, possible values of L will be, all right, let's say if will be 0, 1, and 2. You see that? That's how you interpret the second bullet point, that values for L are integers ranging from 0 to n minus 1, depending on the given value for L. Let's say the last one, if it is if n equals to 7, possible values, right? Values of L will be 0, 1, 2, 3, 4, 5, and 6. It goes all the way to n minus 1. So you got to have the value for n before you determine the value for L. So these are the letters used, and I've explained to you. You have seen this before. We will see also in electron configuration, and this has to do with the shape of the lines in the line spectrum for hydrogen. If it is sharp, they use S. And if L is 0, it's S. If L is P, I mean L is 1, it's gonna be P. If our value for L is 2, that is the D orbitals or F orbitals. Okay. We also have G for 4. G for 4. M's of L, we read this as M's of L. This one, M, you read this as M of L. M's of L. M's of L. Take the values. Minus L all the way to positive L. Let's take the values L minus L, but what does this represent? It's the orientation, all right, on the 3-dimension. Magnetic quantum number represent the orientation, if it is along the x-axis, if it is along the y-axis, or c-axis. Possible values include negative L to positive L, I'll go. You like to go with negative L to positive L, is fine. Let's see how you interpret it. Suppose M of L equals to, or rather, we know if L equals to 1, for example, therefore, M of L will be negative 1, 0, positive 1, because it's ranging from negative L to positive L. Here is L, therefore M of L will range from negative 1, 0, and positive 1. So these are the possible values. If, all right, if L equals to 3, for M of L will be negative 3, negative 2, negative 1, 0, 1, 2, 3. And each represent the orbital. So you gotta be careful. The value for L determines the possible values for M of L. You read that as M of L. Remember to include the word, to include the 0. On a given up to 1s3p 7 orbital and so forth, of which p, you know, p represent 1 from the previous slide right here. P represent 1, and this will be negative 1, 0, and positive 3. So if p, we know we have 3 orbitals. There are 3 orbitals. So these orbitals with the same value n form an electron shell. What do we call the shell? You know, when we talk about the shell, this is shell number 1, n equals to 1, n equals to 2, n equals to 3. This is shell number 3, shell number 4. So if they have the same value, we say that they belong to the same electron shell. We have our subshell, all right? We have subshell based on the shell number. Table 6.2 relationship. Let's see this relationship between the principal quantum number, which is the shell number, possible L values, designation of the subshell, and the possible values for M of L, number of orbitals in a subshell, and the total number of shells. This will be handled down the line when we write the electron configuration of atoms, okay? Electron configuration of atom of different elements. We will have to know the subshells, how many subshells. One thing to note here is the number of subshells equals to the shell number. Shell number 1, we have 1 subshell. Shell number 2, we have 2 subshells. Shell number 3, we have 3 subshells. Shell number 4, we have 4 subshells, all right? This will just take the values from negative to positive L. Let's see, in what example 6.6, there is 1 4s orbital, L equal to 0. I think that is just from the previous page, but I want to look at practice exercise 1. An orbital has an n value for an m's of L. What are the possible values for of L for these orbitals? For this orbital. So we know L equals to 4. Now, possible values for L will be 0 all the way to n minus 1, which is 0, 1, 2, all right, and 3. These are the possible values for L. M's of L, if we take L to be 1, and then M's of L will be -1, no, 0, and then 1. That's why we are given this. We know the value for M's of L. But all you have to start with is focus on the N and the possible values. Sorry about that. You didn't see this. This is what I was writing down, that if N equals to 4, possible values for L ranges from 0 to -1. It is based on what we looked earlier on here, that L allowed values for L, all right, ranges from 0 to 1 minus. So that's what we need to know for this magnetic quantum number. Now let's see how many for practice exercise 2. What is the designation for the subshell with n equals to 5 and L equals to 1? Remember, for this, n equals to 5, L equals to 1. Remember, value and letter, designated letter. Zero is S. You need to learn this. 0 is S, 1 is P, 2 is, 3 is F. So you need to learn this. This is what I'm trying to show you, that the values 0, L, and from here, what is the designated value? And this is 5, B. So this is 5. You'll write that 5B. You'll write that 5B because we know L is +1 and L represent L value. L value is 1, so 5B. How many orbitals are in this? There are 3 orbitals. All right, there are 3 orbitals. Remember, this has 1 orbital, B has 3 orbitals, D has 5 orbitals, F has 7 orbitals. The number of orbitals increase in odd number sequence: 1, 3, 5, 7. That's the maximum you will be given, or you will handle. SPDF, number of orbitals: 1, 3, and 5. So there are, for this question, practice exercise 2, which is P, we have 3 orbitals. Indicate the M's of value. So we know L equals to 1. Values for M's of L. If L equals to 1, M's of L equals to -L all the way to +L, which is -1, 0, and 1. So these are the possible values for M's of L, Let's see, here is a question on what are the possible values of L in L take the values 0 all the way to n minus 1, which is negative. No, this cannot be that. I guess there was a typo here. Let me see. This will be, T should be negative 3. What are the possible values for L? So if in this case, n equals to 4, L equals to 0 all the way to n minus 1, which is 0, 1, 2, and 3. 0, 1, 2, and 3. I think C is wrong. Because we have 4. D is wrong. Yeah, I think D is correct because we have 0. It can be 0. That's possible. I know we don't have 2 there, but that's okay. A is wrong. C is wrong because there is 4. All right. So if you look at this, we have 4. Yet we know L take value 0 to n minus 1. This is wrong as well. So let's see. For question 2, how many different values of M of L are possible in five F? You need to know, all right, you need to know the value for L and the letter here. Designated 0, there is S. 1, there is P. 2, there is 3. And then SPD, 3 is right here. So if L is 3, M of L is negative L all the way to positive L, which means it's going to be negative 3, negative 2, negative 1, 0, 1, 2, 3. So if you count this, this is 1, 2, 3, 4, 5, 6, 7. And the correct answer is B. We have 7 different values for M's of L. M's of L. So the key thing here is knowing that letter F represent 3. Okay, letter F represent value of L of 3, and M's of L take negative L to positive L, negative 3 all the way to positive 3. We have 7 possible values for M's of L, for M's of L. Oh, we haven't talked about this. Oh yeah, we talked about the shape, but here is a question on understanding what each of the first 3 quantum numbers represent. Remember, principal quantum number represent energy. All right. L represent the shape, M's of L the orientation. So 3 things. 3D space. So the dash quantum number define the shape. Psi, we don't have that. All right. Principal quantum number, this is the energy. All right. That is the energy. Spin, we haven't talked about spin yet. We haven't talked about the spin yet. All right. We're gonna talk about the spin, and the correct answer is angular. We haven't talked about the spin yet. Magnetic, we don't have that. Principles represent energy and angular momentum. There are dash orbitals on the third shell. How do we know? Do we need to memorize this? I want to give you one formula to determine the number of orbitals. Note All right, you got to take note of this. This is going to help you. Note, all right, number orbitals is given by n squared. Number of orbitals within a shell. Maybe I should have said number of here. Should have say total number of orbitals within a shell is given by n squared, where n is the principal energy level. So in this case, we will say it 3, therefore 3 squared is equals to 9. 3 squared is equals to 9. So the correct answer for this is C. The correct answer for that is C. All right, C is correct. If it was second, then we'll say n equals to 2. Therefore, our orbitals equals to n square, which is 2 square, which is 4. That's to find the number of. And then our total number of electrons within the energy level is given by 2n squared. 2n squared. That will work. All right. That will work for total number of electrons within the energy level. Now, number of sublevels. Key things here: number of sublevel equals to level what? Level number. That is level number 1, level number 2, level number 3. But for this particular question, you have to use this. N equals to number of total orbitals is given by n equals to 2. And that marks the end of section 6.5. Please read. So far we have looked at 3 quantum numbers: principal quantum number n, angular momentum, all right, angular momentum, and the spin. You have to know all these 3 right here. These are magnetic quantum number, m sub L, angular momentum, all right, there is the angular momentum, and the principal. Remember what I said, we have 4 quantum numbers. And first, before we look at the 4th quantum number, the spin, let's look at how we represent orbitals. And the orbitals, we have p orbitals, we have s orbitals, we have d orbitals. The simplest of all is the s orbitals, which are spherical in shape. So s orbitals, these are spherical. They are like a sphere, like this. They are like a sphere. I don't know if you can see that. Yeah, you can see that. It's just like a sphere. You can see here, these are the spherical. They are the spherical shape. These represent region of space within an atom where there is likelihood of finding an electron. So they are spherical in shape. As the n value increase from 1, you see the shape also increases, or the radius get large. Well, we can represent in 3 dimensions the shapes of orbitals that where there is high region of finding an electron within the nucleus within an S, it is radius in angstrom. It's getting larger for 2s, 3s, and so forth. So these are the S orbitals. S orbitals. As n increases, likewise the radius increases for the nucleus in angstrom. P orbitals, they represent, or they are dumbbell. It's just like two shapes. See, it looks like a dumbbell, two loops pointing. This represents there is high probability of finding an electron here and here, with this being the nucleus. Most commonly, you will see in the problem the S orbital, which is spherical, and the P orbital, which is the dumbbell. You see, this is just illustrated using the orientation in 3D along the Z-axis, along the X-axis, and along the Y-axis. D orbitals, they are clove, 4 loops. All right, 4 loops pointing in different direction, right? F orbitals, they are complicated, and I don't want to get into details so that this is the kind of questions you'll see in an exam, that dash orbitals are spherical. What I wanted you to remember is the shape of orbitals. They are spherical in nature, symmetrical. So the correct answer here is A, spherical in nature. For B orbitals, they are what? They are dumbbell. They are dumbbell. Now, looking at the energies of hydrogen atom, assuming that this portion represents the nucleus, as you go away from the nucleus, the N value keeps on increasing all the way to infinity. This represents the shell closest to the nucleus, and each box represents an orbital. Remember what an orbital earlier on I described, region of space where there is what? There is likelihood of finding an electron. The number of orbitals increase in odd number. So in shell number 2, we have 2 orbitals. In shell number 3, we have 3 orbitals, 3 subshells, not orbitals. So here are 2 subshells, 2s, 2p, 3 subshell, 5 subshell. This is S subshell, P subshell, or sublevel, and each box represent an orbital. Later on, where we are going with this is we'll write electron configuration. And remember, for hydrogen, it's only for what? For a single electron. Hydrogen has only 1 electron. There is a term here chemists use to describe a set of orbitals, degenerate. What do we mean by degenerate orbital? Degenerate orbitals are orbitals with same energy. Using this third shell, we call these orbitals degenerate because they have the same energy. In other words, shell number 2 is lower in energy compared to shell number 3, and we can say that 2p is lower in energy compared to 3p. We call these degenerate orbitals, orbitals with the same energy. We're gonna be using the degenerate down the line. Even in chapter 8, we will use degenerate and understand what that means. So as the number of electron increases, so does the repulsion. Why do they repel? Because they are negatively charged. Positive, positive repel. negative repel, and that is why we talk about electrons repelling one another. Therefore, in atoms with more than one electron, not all orbitals on the same have degenerate. This is now the explanation behind several lines. If you go back to the line spectra for multi-electron, it's explained here that not all orbitals within the same energy level have the same energy. That explains why there were so many lines. So here, orbitals, a set of orbitals with same energy are said to be degenerate. Degenerate means they have the same energy. Lastly, before we look at the electron configuration, the fourth quantum number is the spin, all right? The spin quantum number, and this was proposed by a Dutch physicist. Forget about the name. He proposed that electrons spin in opposite direction, and this is in line to what they observed at that time about, why do we have several lines for a multi-electron system? Here it turns out that two electrons occupying the same orbitals have different spin. They spin in different direction. Look at the spin, look at the spin, causing the splitting, okay? Into electron in the same orbitals do not have exact same energy because of this spin. In the magnetic, we call this m's of s. Remember, m's of L, this is m's of s, and S stands for the spin. So therefore, we now have four quantum numbers: principal, the angular, the magnetic quantum number, and the spin quantum number. And this is just has to do with the spinning of an electron or electrons. There are only two possible values. There are only two possible values, and this is plus half and minus half. Let me illustrate this. You may have seen this, and you will also see this. When you write the electron configuration, there are two arrows pointing in the same direction, and basically they represent the spin quantum number. We can consider this as plus 1/2, and this is minus 1/2. Right? Quantum number 4 is the spin quantum number. Oh, well, before we get to electron configuration, having established that electrons occupy energy levels, and within the energy level, we are sub-levels, looked at the 4 quantum numbers. Pauli's exclusive principle, all right? This is a principle which explains the behavior of electron when two electrons in the same atom have same set of, or no two electrons, rather, no two electrons. It is a statement of Pauli's exclusion principle. No two electrons in the same atom can have the same set of 4 quantum numbers. Remember, the 4 quantum numbers should be able to describe or explain Pauli's exclusive principle, which is crucial when we get to electron configuration. Therefore, there are no two electrons in the same atom that can have exact same energy. This means that every electron in an atom must differ by at least one of the 4 quantum numbers. Can be n's, can be angular, magnetic, or the spin, at least one of them. They cannot have all of them. What I've highlighted here is the statement of Pauli. You may see, I cannot promise, but it could be in the upcoming exam. And if you don't know who did what, because we're going to talk about the Hans rule in the next section, all right? So now let's see electron configuration. Electron configuration is simply how electrons are, section 6.8, how electrons are arranged within an atom. Properly, arrangement of electrons in an atom, and there are three methods. Please remember three ways or method. Electron configuration. If you can nail out this, it's gonna help you out because you may be tested in one. You should be rounded in all three ways of writing electron configuration. What are the three, all right, what are the three ways? I call it the long way or whichever way you want to call it, so long as you know how to write electron configuration of elements. Okay. So first, electrons occupy orbitals according to increase in energy level. It's just like having a 110th floor building with no elevator. It makes sense that you will occupy maybe the room or floor closer to the ground floor so that you don't have to walk all the way to 110 with no elevator, because by the time you get up there, you'll be tired because you'll be using a lot of energy. So likewise, electrons occupy the lowest energy level before occupying the highest energy level, or orbitals in the highest energy level. There is a pattern here which will help you out, which some of you may know, using the Apophis principle. All right, use this, you may see state started. Remember this. In crown, and I've seen the crown state, all right? In crown state, that means lowest energy level on atom or ion, electrons. Electrons feel the lowest available energy, and then they feel the subshell of higher energy, This is the key to understanding the electron configuration. Please, to understand this principle, learn how to reproduce this graph. I'm just going to blow up this so that you see how I'm going to reproduce this 1s2, 2s2, 2p6, 3s2, 3p6, 3d10. If you look at here, let's see first of all, complete is 4s2. 4p6, 4d10, 5s2, 5p6, 5d10, all the way to and then here is 4f 14, 5 of them, and then 6s2, 7, no, 6p6, 6d10, 6f14, all the way to 6 of them, and then 7s2, 7p6, 7d10, 7f14. Indeed, you have 7 of them. These represent shell number 1, shell number 2, shell number 3, shell number 4, shell number 5, shell number 6, shell number 7, according to shell number 1, 2, 3, all the way to the output level. Now, once you have and place plan, if you look at shell number 1, we have 1 sub-level. Shell number 2, we have 2 sub-levels. Shell number 3, we have 3. Shell number 4, we have 4. 1, 2, 3, 4. Shell number 5, we should have 5. 1, 2, 3, 4. And that is why I have a dotted line here for 5. 6, I shall have 6. 7, I shall have 7. From here, you draw a parallel or cross out with an arrow. You start with 1, 1, and then I'm going to join 2 of them, and then you come 3 of them, 3 of them, and then you come 4 of them, and then you go 4 of them. You now join the head with the tail, the head with the tail of an arrow, and with the tail of an arrow, and with the tail of an arrow, and with the tail of an arrow, like that. If we want to start here, all right, start and then end at 7s2. This is end right here. We will write this one. Look at this. 1s2, and remember the superscript represent maximum number of electrons. 1s2. 2s2, 2p6, where I am is 1s2 here, and then I come to a, maybe I should minimize this so that we look at it. So 1s2, 2s2, 2p6, 3s2, so 2p what? So 3s2, 3p6. After 3p6, is 4s2, 4s2. And then notice, after 4s2 here, 4s2, we go to 3d10. So here is 3, or here 3d10. And then after 3d10 here, we 4p6, 5s2. So 4p6, 5s2. And then after 5s2 here, we go to 4d10, 5p6, 4d10, 5p6. And then after 5p6, 6s2, 6s2, 4f14. So 6s2, 4f14. And then we come to 5d10, 6p6, 5d10, 6p6, and lastly 7s2, 7s2. What I've arranged here is according to increase in energy. Here is increase in energy. What I've done here is I have arranged the subshells according to increase in energy. Don't think that you are done with the 3s and then you go to the 4s and then you go to the 5. I know from math makes sense that you start with 3 and then you go to 4 and then you go to 5, but there is an overlap when it comes to arranging the subshells according to increase in energy. For example, you interpret this as 4s, all right? 4s is lower in energy compared to 3D. I know you'll be like, how comes that 4 comes before 3D? It is explained in terms of energy. So likewise, 4p6, or rather 5s2 is lower in energy compared to 4d10. You cannot have the 4d10 and then 5s2. Even 6s2 compared to 4f14, this one is lower. So please learn how to start from here. All right, start from here so that you can reproduce this. Once you have this, the numbers here represent the maximum number of electrons. And maybe I should have started from here that 2, if you look at how it's increasing in 4, 4, 4, 4. 2 plus 4 is 6. 2 plus 4 is 6 plus 4 is 10. 2 plus 4 is 6 plus 4 is 10 plus 4 is 14 and so forth. So there is a pattern also here, which you can use in order to write the order in which electron occupy this sublevel according to increase in energy. This will give you the right electron configuration. And the superscript numbers represent electrons, which means this can take a maximum of 2, can take a maximum of 2, can take a maximum of 3. Now, here, the most stable organization is the lowest possible called the ground state. So we use this to write the ground state electron configuration for element. For example, for P5, all right? 4 represent the energy level, P sublevel, superscript number of electron. Later denoting the orbital, if it is d orbital, f orbitals. The superscript of chaos, I've explained that it represents the number of, or maximum number of electrons. It's not really going to be what it should be. For example, hydrogen, right? Electron configuration is just gonna be 1. So here, superscript denoting the number of electrons in those, and these are just maximum. These are just maximum. Like for example, for P5, that means we have 5 electrons, but everywhere we have p orbitals, we can have a maximum of 6. Sometimes in some element, we can have 2 electrons in p sublevel, but here, these are just maximum. So before we look at this orbital filling diagram, let's say you want to write the electron configuration for hydrogen. Hydrogen is number 1, all right? Hydrogen is number 1, and this will be 1s1. Helium is 1s2 because it is atomic number 2. Lithium is 1s2, 2s1. We add the superscript numbers to correspond to what? To correspond to electron configuration. Let's see sodium. Sodium is number 11, all right? So number 11, that means we have 11 electrons, 1s2, 2s2, that means 4 electrons so far, 2p6, that means 10 electrons so far, and 3s1, 3s1. You see how I've written the electron configuration? Pi. Using this arrangement, I'll add the numbers here so that it corresponds to atomic number. 2 plus 2 is 4, plus 6 is 10. I only need 1 for sodium number 11. And this is just the ground state, the easiest way. I call this is one of the methods. Remember, I say there are 3 methods. So that is the ground state. I will call this here method 1 here. This is method, we shall have this is method, this is method 1, okay? This is method 1 right here. The first method. Let's say calcium. It's number 20, so it's gonna be 1s2, 2s2, 2p6, this is 10, 3s2, 12, 3p6, 18, and then 4s2, which is 20. Electron configuration. This is the ground state electron configuration. There is the orbital filling diagram. All right, method 2 here is orbital filling what? Orbital filling diagram, orbital filling diagram. In this case, arrows represent electrons. I want you to understand what arrows represent. The box represent an orbital. Look at this orbital. Remember what I described earlier on. Orbital is a regional space where there is likelihood of finding an electron, where there is likelihood of finding an electron. So this is an orbital. I'll call this orbital. You can take note of this while we are here. An orbital can take a maximum of 2 electrons. It can have one such as this one. So you need to know this. You need to know the long form of writing electron configuration so that you write the second one. For example, here, chlorine, for example, which is number 17, is 1s2, 2s2, 4, 2p6, that's 10, 3s2, that's 12, 3p5, that is the electron configuration. So using the second method, I'll have this 1s2, this is 1s, this is 2s, 2p. Remember there are 3 orbitals, 3s, and then 3p. So here we're gonna have 1 pointing up, pointing down, pointing up, pointing down. We have 4, 5, 6, 7. Remember, electrons are simply distributed fast before you start pairing them up. We'll see that that's called Hans rule. We're gonna see at the Hans rule, right? They face up, they can face down before you start pairing them up. So here I have 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. I singly distributed fast before start pairing them up. So this is the orbital filling diagram for chlorine. Sometimes you may see this 1s, 2s, and then 1, 2, 3, this is 2p, and then this is 3s, and then 1, 2, 3, this is 3p. And the electrons will just be the same. You see this? And then for degenerate, you just have to pair them up once you singly occupy them. Once you singly occupy them, it's the same thing, orbital filling diagram. The arrows represent, or half arrows represent electron. It can be a full arrow, it can be half, but remember they must have opposite direction for opposite spin. This is what I was explaining, or what I was practicing here by singly distributing the electron fast before start pairing them up. This is the Hans rule. If you look at this electron configuration of carbon, for example, which is number 6 on the periodic table. So given the periodic table, you should know how many electrons are there. Atomic number represent the number of electrons for a neutral atom, unless it is an ion. For a neutral atom, atomic number represent the number of electrons. So carbon is number 6 on the periodic table with 6 electrons. And if you look at the electron configuration from the Hans rule, when filling the degenerate, remember what we say, degenerate have same energy, they are singly distributed fast before you start pairing them up. Before you start pairing them up. This is electron configuration. This is an orbital filling diagram, electron configuration. So these are 2 ways. This is the method 1 I showed you earlier on, and this is method 2, which is orbital filling diagram. The before we look at the third method, lowest orbital energy is reached when the number of electrons with the same spin is maximized. This describes the Hans rule. It describes the Hans rule, right, which we just talked about. Hans rule. The correct answer is E. Heisenberg uncertainty principle, we looked earlier in part A. Please read that. You'll see this later on. Pauli's exclusive principle is about 2 electrons in an atom cannot have all 4 quantum numbers being the same, but the electron having the same spin being maximized is a statement of Hans rule. All right. Now, practice exercise 1 on example 6.7. How many of the elements in the second row of the periodic table, lithium through neon, will have at least 1 unpaired electron? At least 1 unpaired electron. This will call for writing the electron configuration. A, 3, 7, and D. All right. So you have to write 1s. You have to write the electron configuration for all of them. That means second row, lithium, beryllium. All right. Boron, I'm looking at my periodic table, carbon, and see which one will have unpaired electrons. I'm not going to write, you can do on your own and see which one will give you unpaired electron. You can do that. Number 2 here. Write the electron configuration for silicon. Silicon is number 14, all right? In its ground, how many unpaired electron does it have? You can do this. I want to do this. Let's see. Crown state. Silicon is number 14. This is silicon on the periodic table. That means it has 14 electrons. And since we are looking at the unpaired electrons, unpaired, you have to use orbital filling diagram, which is here 1s, 2s, 2p, 3s, 1, 2, 3, 3p. This will have 1, 2, 3, 4, 5, 6, 7. They are degenerate, so they must be singly occupied first before you start pairing them up. Answer. So far, I have 10. I need 14, 11, 12, 13, 14. They are singly distributed first before you start pairing them up. The question here is, how many unpaired electrons does the ground state? It is obvious. Look at how many electrons are unpaired. These are unpaired what? 2 unpaired electrons. There are 2 unpaired electrons in the ground state of silicon, So please work more on writing electron configuration. You should be able to write the ground state using the long method, using the orbital filling diagram. Now, the condensed electron configuration uses group 8 element right here. Third method here is condense. Condense is 2. Make it small. Condense electron configuration. Condensed electron configuration. I call this short hand. It uses the shorthand to write electron configuration. This is not 8, but I meant to say shorthand. Okay. This uses group 8 element to show or indicate core electrons. The core electrons. Core means inside. Now, there is what we call valence electron here. Before we look at that, what are valence electrons? These are electrons in the outermost shell. Or electrons with highest n value. That's how you identify the valence electron in an atom. For example, e.g. for sodium, which is number 11, if you look at electron configuration 1s2, 2s2, 2p6, and 3s1, we say that there is one valence electron because that is one electron in the outermost shell, shell number 3 here, highest n value. Therefore, what? One valence electron, one valence electron. Magnesium is number 12. So this is 1s2, 2s2, 2p6, 10, 3s2, and there are 2, therefore 2 valence electrons. The rest we call it core electron. So when we say valence electron, electron in the outermost shell. And for main group elements, which you should know what is meant by main group. Main group or representative group those are the groups on the periodic table numbered using Roman numeral and letter A. Number of valence electrons equals to group what? Equals to group number. So if I use this, for example, all right, magnesium is in group 2, and we have 2 valence electrons. Sodium is in group 1A, therefore it has 1 valence electron. So all group 1 will have 1 valence electron. All group 2A will have 2 valence electrons. All group 3A will have 3 valence electrons, except for group 8. Helium has only 2 electrons, but the rest have 8 valence electrons. 8 valence electrons. Now coming back to, I was explaining the valence electron, coming back to condensed state, and how do you write the condensed state? We use group 8, all right? We use group 8 element to indicate the core electron, and then we just write the valence electron. Otherwise, if you don't write the long way the way I have it here, you won't be able to see the valence electron. All right. For example, the one we did earlier on for silicon, this was for silicon, right? We can write the electron configuration by saying core electron is represented by this, which is 10, by saying neon, and then writing 3s2 for this and 3p2. So this is the shorthand, all right? We're just gonna write this for 14 silicon is equals to neon represent 10 electrons, and then 3s2, 3p2. Here are 10 core electrons, 10 core electrons. And what you see here are 4 valence electrons, 4 valence electrons. So 4 valence electrons. What determine which, or how do you choose which element to use? You look at the element in question and then you step back on the periodic table. Maybe if I use the periodic table here, show you using the periodic table, all right? I want the periodic table of elements, all right? So here, using the silicon as an example, if you look at silicon is right here, I'll go step forward all the way to the rear, that is neon. that will represent the core electron. So you go back one row, go all the way to group A, that will be the element which will represent the core electrons. Count how many electrons are in there, and then the rest will just be the core, will just be the core, what will just be the core electrons. So I want you to know how to, all right, select group 8 element to use that. That will give you the electron configuration. So if we look at the fluorine, you go back, helium represent 2 electrons, plus 2 is 4, plus 5 is 9. Fluorine is atomic number 9. Look at chlorine, step back one row, go all the way to group 8, and this is neon. We have 10 electrons. These are the valence electrons. You still need to know how to write the long form, you know, the 1s2, 2s2, so that you see these core electrons. You see those are core electrons using the group 8, and the valence electron. We represent these valence electrons. All right, let's see, there is a learning check here. What is the question here? Which group of element is characterized by this electron configuration? Don't worry about the numerical value of n energy level. That means the principal energy level. What is important is the superscript numbers here. When you add these two numbers, you end up with 4. That means these elements belong to group 4, 4 valence electrons. Remember what I said, group number for main group element represent the number of valence electrons, the outermost shell, So for this is group 8, and I think it is krypton for this, a certain atom mass and this electron configuration in the outermost. We care less about N, but S2 and P6, adding those electrons gives you A. So the only element with group 8, unless you don't know what these elements are, krypton is in group 8, it's number 36. Krypton is number 36, and that's the correct answer for practice exercise 1. Let's see, current state electron configuration for fluorine. If you look at this, you still need to know the long form 1s2, 2s2, and helium represent the core electron group 8. How do we pick up that? It's based on what I explained earlier on here, that for fluorine here, I'll go back one step and go all the way to the end. This is helium, and helium is number 2, which means it represents 2 electrons. The remainder of electron, which is the core, should add up to 5. So 2 plus 2 plus 2 is 6. It's not correct. 2 plus 2 is 4 plus 3 is 7. It's not. 2 plus 2 is 4 plus 8. That's not correct. The correct answer is D. 4, 9. The correct answer is D. So remember to learn all the 3 methods of writing electron configuration. Let's see, what are the transition metals? You know, transition metals are these elements on the periodic table on this region, this depression right here. They are the transition metals. These are the inner transition metals. How do we write electron configuration for this? How do we write electron configuration for transition metals? You still need to understand that degenerate orbitals are singular occupied. Remember the feeling of electrons, 4s comes before 3d, all right? This goes to splitting. And without memorizing this, I want you to learn this function right here. This is what I want you to learn, how to reproduce from here. All right. If you look at the transition metals now, the transition metals here, Argon is group 8 for manganese. In shorthand way, we have 18 electron. Manganese is number 25. So here is 18, 20, 21, 22, 23, 24, 25. Using the periodic table, this is manganese. This is zinc. Do you know the atomic number for zinc? Look at the periodic table. 30. We have 18 here plus 2. It's 20 plus 10. And remember the 4s comes before the 3d. All of them, they are singular occupied. All of them, they are singular occupied. Having gone through that, what I want to finish up chapter 6 is the exception. There are exception. Please read that on electron configuration. Read that on electron configuration. Before we look at exception on electron configuration, periodic table, all right? Periodic table can also be broken down according to the last electron, all right? According to the last electron, which goes in the subshell. For example, when I write electron configuration for example, calcium here, let's say this, I'm just going to blow out this calcium here. The last electron goes in the 4s right here. You see, it's an s block element depending on which electron. We have the s block, we have the p block, we have the d block, and f block. So how many? 1, 2, 3, 4. We have 4 blocks, and this has to do with what? The last electron which goes in when you write the electron configuration. You can do that and see the main group. Question from here is, which one of the following is an S block element? Which one of the following? You will not really have this periodic table. Let me just be honest with you. I will not give you the periodic table you see here on the PowerPoint, but I will expect you to write the electron configuration and see which sub-label is being occupied by the last electron, and that will be the block for that element. All right. Now, some anomalous or abnormal electron configuration on the periodic table. There's some abnormal electron configuration on the periodic table, which doesn't follow the conventional way. What we mean by anomalous, all right? What we mean by anomalous. For example, within the first of the element, there is the chromium, which is number 24, Cr, which is 24. I know you'll have expect this, all right? This is 24. You'll have expect 1s2, 2s2, 2p6, 3s2, 18 4s2, 20, 3d4, and copper. Copper. Which is 29, you'll have expect that 1s2, 2p6, 2, 3d6, 18, 4s2, which is 20, 3d9. But it turns out that they don't follow this pattern right here. We cancel that, and this is the electron configuration. 1s2, 3s2, 3p6, 3s2, 3p6. No, 3, yeah, I messed it up here. This should be 2s2. 2p6, 3s2, 3p6, yes. 4s1 and then 3d5. This is the correct electron configuration for chromium. Likewise for copper, gonna be 1s2, 2s2, 2p6, 2, 4s1, 3d10, 3d10. This is 3d10, and this is the correct electron configuration for copper. It's anomalous, some irregularities. What really determine this is what I've just observed with other element on the periodic table is, if you look at this, what is common? D4 and D9. This is almost half filled, all right? So you elevate one electron to make it singly occupied. The D5 has 5 orbitals, and all of them, when you promote one, they are almost all the same. They are like degenerate orbitals, and we have it 4. So remember, D4 D9 rule, which means if you just do the way we do, and then you end up with the D4 being the last electron, you promote from the previous subshell to make it 5. If it was D9 on any other element on the periodic table, you make it D10, closer to that. D5 is half of what? Half of 10. Remember 10 electrons. If you have 5 electrons, D take a maximum of 10. So half and full. It works. I just only want you to remember that it's not always that we follow the conventional way. With that, I just want to say thank you. That is the end of part P of chapter 6. I'll see you again in, all right, in chapter 7. I want you to read chapter 6, make your own notes, complete the assignment on MyLab and mastering before taking the quiz. Use the mistakes you'll make in the homework assignment as a learning practice, so that it's going to be easy for you to complete or to do well in the midterm exam. So I've just explained what the anomalies. Other than that, assignment will be posted online. See you again next time. Thank you.